Hi guys, can I get a sound check?
I can hear you.
Okay, great. How come let me see where the MacBook Pro microphone. Sorry guys, I can't. You guys ever heard the statement, the enemy of good is better, or better is the enemy of good?
I don't think so.
No? Well, there you go. I'll be the first to introduce you to that concept. That if something works, just leave it alone. Okay, let's see guys, just give me a second here to get myself organized. Meetings. Share content screen. So let's see here. So first, guys, I was going to be talk a little bit about the project. If I can, let's see if I can find, where did I put the project? Okay, so these were just sort of my crazy notes here. So the first thing was, I think Logan, I was going back and forth with Logan about some questions he had about, I think Logan, correct me if I'm wrong, but it was about this first, you were sort of at this first step, is that correct?
Yeah, because it kind of determines the rest of it and had to do with choosing the unit width that you're going to start with.
Yeah. So, just first thing is just remember that that basically, although these X1s, X2s don't mean larger than unit size, these numbers do. These numbers below. So, God, what's a good color here? Anyway, I'm just gonna stick with blue. So these numbers mean these are the transistor sizes that you guys should be using. So let's for the sake of discussion, let's say I wasn't sure what the answer is to Logan's question, and I didn't work it out, but let's try to work it out together. So let's say if I'm looking at this guy, and let's say we call the unit size NMOS in this process to be width of 300 nanometers and length of 0.18 micron or 180 nanometers. So what this first guy would be, X1 would look like W over L of 0.3 over 0.18 microns. And the P would be W. So this would be like M is equal to 1. This would also be the same. I think this is the cleanest way to do it. I hope you guys see what I'm kind of doing here, and then with m is equal to 2. Are you guys familiar with m factors? Were you guys using this in your simulations?
I was just going to manually enter the numbers.
Okay, just what's that? Sorry.
I was just manually entering the sizes.
So you were going like W over L of 0.6. Is that what you were doing?
Yeah, basically.
Okay, I think this is probably, so this is, the thing is a lot depends on the computer models. Okay, sorry, the CAD, the SPICE models, but strictly speaking, like if you had an M, so I'm going to spend a lot of time on this because I think it's actually like good stuff. But let's say you had a, let me actually pop open a, so do a new one. Squared, let's do squared. Okay, so strictly speaking, this is what like if I was going to do the layout of this, let's just for the sake of discussion say this is your NMOS, and the width is 0.3 micron and the length is 0.18 micron. Okay, so when you do a something like m is equal to 2, what happens is you are basically saying, I'm going to have 2 of these guys. Just letting me do this. No. I'm going to have 2 of these guys connected in parallel. So I'm going to, connect up the gates. I'm going to hook up, use a metal line to connect the sources, and I'm going to hook up a line to connect the drain. Something like this. This is all like very conceptual, right? But then each one of these devices, so we're not modeling any of the interconnect, so we're not modeling the this capacitance, we're not modeling this capacitance or resistance. So in fact, when you say this in SPICE, when you say this would be the equivalent of m equal to 2, this would be the equivalent of m equal to 1 in SPICE, this will have twice the capacitance, say, as this exactly. This will have half the resistance of this exactly. Okay, so that's, if the other way to do it would be to say, I'm going to have like this guy, and this one would have a width of 0.6 micron and a length of 0.8. And this would not have the same, like it would not exactly have half the resistance of that, or would not have exactly twice the capacitance of that. The reason is because, sort of going back to our second order effects, like, as this thing gets to be, going from a close to a minimum size width to twice that size, your actual threshold voltage will be slightly different. Your, this capacitance of this area is not going to be the same as 2x the capacitance of that area, because this will have the sidewall, twice the sidewall, and twice the area. This will have like not twice the sidewall of this quite. So this is, long story short, this is not exactly the same as this, as 2x of that. Now, if you, there's no penalty for if you just want to do this rather than that. I think it's cleaner, to do to do the M factor route. So that way you're sure if you're building something that's like going from this guy to, sorry, this guy to this guy, you're at exactly 4 times the size, if that makes sense. Again, it doesn't matter. I don't know. Logan, are you doing it in LT Spice or using P Spice?
Yeah, I just had the total realization of what you meant by that. So the M factor, because we're just paralleling them. So you're just basically saying the amount of parallel devices. So like on X2 there, you have 8 paralleled PMOS and 4 paralleled NMOS, right?
Yeah, and then you're guaranteed to be exactly doubling up the size from X1. Sorry, not doubling up, quadrupling from X1 into X2, and so
Okay.
on and so forth. So I
Yeah, no,
think it's a
the
little
Spice is
point
great about
there.
paralleling stuff.
Yeah, so if it's easy to pass the parameters, I would go with that route. I would use the M factors. If you find it, I keep forgetting. I don't use LT Spice enough to remember from semester to semester how easy it is to deal with the M factors. But I would go that route, and there's like less a possibility for something like some second order effect that might confuse your calculations. If you just make the sizes, it's not going to be like any points off or anything. I just think it'll be like cleaner that way. So, but anyhow, however way you do it, I would go, so this guy is this minimum size, and then it's the X2 is actually this exactly the same thing, but same size, but the M factor would be, as we're discussing, is, so WL is 0.3 over 0.18 microns, micron over micron, but its M factor here would be 8 for the PMOS. So it'd be this guy. And the M factor here would be 4. So you could just sort of copy that over. Okay, so by the time you get to this guy, by the time you get to, man, this is horrendous. Let me actually just see if I can open it in something more friendly. Well, shoot, no, don't do that. Well, it would have been easier to do this anyway. So, so by the time you get to this guy, so this value for this guy, again, this is trying to be the same size as the total input of this. So I guess it was last week, I said, I did a back of the envelope calculation, and I said, okay, the total input of this guy is this number, right? It's assuming we started with a 0.3 micron wide NMOS. This guy is going to be a 32 micron wide, so this will be the size of the NMOS. This is the size of the PMOS. So, by the way, guys, since like you're going to be in the middle of this project, and so this is not the time to be shy if you don't understand anything I'm doing. So quite jump in and ask your questions, because you're going to be stuck if you're not following what I'm saying, or if I just don't make any sense. So let's say, let me just run these numbers. So it's 0.3 times 32. So it'll be like 9.6 micron wide for the NMOS. That's the total width of the NMOS, because I have 32x 0.3 micron wide devices, and I'm going to use, the assumption is I'm always going to use minimum length NMOS and minimum length PMOS. And then, so this guy is going to be 64 times 0.3 So this is going to be 19.2 micron width for the P MOSFETs. Okay, so the total capacitance, so the total width of the device, both N and P combined. So let's, for the sake of discussion, assume C sub G, which is, you know, capacitance per unit width, is the same for NMOS and PMOS. And I claim that it is because they get made, the gates get made for the NMOS and PMOS at the same time in the process. So they're guaranteed to be the same, the oxide is guaranteed to be the same thickness for the NMOS and PMOS. Okay, so I can just add these two together in terms of widths. So 9.6 add, so I get 20.8 microns of total width, okay, for this device. And so we're trying to size this to match this guy by overlapping the transitions in the simulation. So whoops. Did Logan, you put a screenshot on the M factors?
Yeah, it shows the configuration window that you get when you're trying to edit
Yeah.
the.
Yep. So now the question is, can you just pass that from the like in the hierarchy? So you're just keep making a flat hierarchy. You didn't have a symbol for the inverter. So you just have these transistors
2, 3, 4, 5,
in
6, 7
in
MOSFETs.
so you just have these in sort of a flat, that's called, what you have is like a flat hierarchy. So there's no symbol for the inverters where you're passing on these parameters to.
Yeah, I didn't want to
If you
mess
get,
with
yeah. So if you wanted to get more fancy, you could put these devices in there. And I think you can also do, and this is the part I can't remember. I think you could actually put also M factors. So you could just create one thing like an inverter symbol. And I think you could do M factors, but I'm not 100% clear. I'm sure on LT Spice. I'll try to get it working just to double check. But what you did is fine. I mean, the flat is fine if you want to do flat. It's just, if you want to make modifications to your base inverter, you just have to go do it on all your transistor schematics rather than just doing it in one. Do you see what I'm saying? If you just said,
Yeah.
for some reason you decided you wanted the minimum width to be 0.4 microns, then it's a little bit more painful. So anyway, so this is 28.8 microns of total width. Okay, so now if I go and look at my cheat sheet, which is our book chapter, which is, God knows where I have it. Originals, that is, okay, good. Came up pretty quick. So this is the C sub J in femtofarads per micron. Okay, so 1.67 femtofarads per micron. Okay, so I'm gonna try to get back. God, where did I put that guy? Would it be this? Nope, not that. Let's see what I have my recents. Sorry guys, I'm just lost where I was. So I opened it in here, but where did I go? Yeah. Surprise. Okay, so from the book, so I'm cheating here, okay, guys? So just wanted to make sure I'm in the right path. It says that C sub G is 1.67 femtofarads per micron. So I'm totally cheating, working backwards, okay? So my expectation for C delay is that it'll be around 28.8 micron times 1.67 femtofarads per micron, or 1.67 multiply, or around like 48 femtofarads. So if I got that, and assuming I did my calculations right and everything's good, once C delay gets to be 48 femtofarads, those things should be pretty well lined up. Now, it'll be a little different for you than what's in the book. They're using probably a slightly different, like these SPICE models are not like sort of, is not part of some Bible thing. They probably got it from some other place. And maybe their parasitics may be different, so on and so forth. So it could be a lot of different things why it won't exactly be 48 femtofarads for C delay. But if it's like 5 femtofarads or 500 femtofarads, you're probably off. Okay, so that's kind of like, that's how you should use that book result. It just to sort of kind of make sure you're in the right ballpark and you don't have some connectivity problem or some other weirdness. So the actual thing you're trying to do is do it exactly backwards from the way I did it. So what you're trying to do is to play around with C delay, get some number and divide it by this number, by the 28.8, and find, you know, what this should be. And that's sort of the problem you're trying to solve in problem 2. But you have this sort of cheat sheet in the book too, which tells you you're kind of, this is the right ballpark that you're at. And by the way, so this one is only true if you have a minimum length device. So make sure you have your links are all minimum length, so 0.18. Everything, keep everything 0.18. So that was pretty long-winded. Does that answer your question, Logan?
Yeah, it makes sense.
Okay. Anybody else have anything? Any questions? So just again, so once Logan gets, or all you guys get past that point, the same thing is true here. So you're like, you got to make sure you guys sizing stuff up and sort of building up. And this is also an illustration of what we talked about. And we talked about, you know, we went through this pretty quick, but when you're driving a big load, let's say I have a problem that somebody says, hey, you got to drive a picofarad, or that's 1 × 10⁻12 femtofarad. That's a big number in a chip, relatively big number. Notice like a reasonably big device here. This big inverter is only 50 femtofarads. So that's 48 × 10⁻15 farads. So much smaller than, say, this case that I'm trying to drive this picofarad. Basically, what you try to do is you're sizing up and just sort of driving, just sort of drawing like relative size of the devices in this in terms of the widths or the M factors, right? The M factors are going up, represented by the size of this inverter. So this might be M is equal to 1. This is M equal to 4. This would be M equal to 16. This is M equal to whatever, 64 or something. So roughly, it's very, if the most you get the most efficiency in terms of the total delay when these sizes are going up by a factor of 2.5 to 5. It's not exact, but like it turns out, again, we went through it pretty quick and we didn't really prove it, but that's how it goes. So if this is a pretty typical problem, that if you're trying to drive a load like this, you kind of size up in stages by a factor of 2.5 to 4 to 5. That gets you the fastest delay from end to end. This is just how it turns out. So, you know, we talked about this a little bit in the path delay, etc. Okay. Anybody else started the project yet? Everybody's waiting for the morning of May 21st. Yes.
It's gonna start out this weekend.
Nice. Do it, guys. Don't be like me. Don't do as I do, do as I say. Sounds good. Okay, guys. Well, good luck anyway. And I'm actually pretty excited. I feel like this is like the, you know, the whole testing, especially for this class, it just doesn't make sense. I'm glad you'll be spending a little bit. I'm hoping you'll use that to spend a little bit more time on the project, and you know, things might make more sense to you once you do that. Okay, so anywho, so don't be shy. If you have questions, you can always email me or show up in the office hours. So let's get back to where we were, which is our interconnect. And I think this is where we started. So, you know, I think, you know, I think the main thing that I want you guys to think about in terms of the interconnect is, when I was first starting to learn about VLSI, I was very focused on the transistors, and I just had like this view that everything was all about transistors, etc. And I think it's, unfortunately, we're not doing like building a chip or anything, or even a you know, a small subsystem. But, you know, once you start doing the layout, you realize that like most of your chip is interconnect, as a matter of fact. And some of like your biggest problems is the interconnect. You know, the added, like when you're doing analog design, we're not talking about analog design in this class, but once you're doing analog design, you're trying to get precisely valued or precisely matched devices. It's very, very important. Again, we're not talking about that, but it's all like, it's very important analog design. It's like, if you don't do that, again, we're not going to get into it, but you're toast. And so the thing that tends to throw off your matching are these parasitic capacitances of your layout. You're always trying to match the shapes of your interconnect to replicate these parasitic capacitances and crosstalk and all that. Crosstalk is another thing that kills you in analog design, also in digital design. You're a little bit less sensitive, you're actually a lot less sensitive to it, but it still does affect you in long lines, etc. So the thing to visualize in this lecture is that the actual interconnects are just as important as the design of the transistors, and you're actually, as a matter of fact, you're going to spend a bigger part of your design trying to deal with the interconnect, trying to optimize the interconnect, troubleshoot the interconnect, you name it. Like dealing with the interconnect and the routing and all that stuff tends to be the real problematic thing. Okay, so again, we're talking about, you know, most of the discussions in this class also is about the early part of the design. We're trying to estimate stuff, and we came down to this methodology of using this pi models for estimating the delay through an interconnect. And we said, you know, that it does make a very good model. model estimation, just to use 3 of these. This is some kind of magic. I have no proof of why this is the case or why it should be the case, but just 3 of these models are like a very close approximation to a completely sort of distributed model of RC networks. And we had seen how we can use Elmore delay to just do hand calculations of the delay. So, okay, so that's where we were with where we stopped. Now we're gonna sort of parse through different aspects of the interconnect. So we said interconnects had resistance, they have capacitance, and they have inductance. We're gonna ignore inductance. Inductance is really something you only see on chip. You only see it when you have very long lines that are being driven very fast, or on purpose, you're building actual inductors on the chip. Let's say you're trying to build, again, so for analog designs, or you're building antennas or something like that, or oscillators or stuff like that. So we basically, don't look at inductance on chip essentially. So we're not gonna get into that here. Now, a word to, just a warning for a lot of you guys are probably gonna, and we do too, chip design, you're like putting your chip into some printed circuit board, and there the inductance is a very big part of the interconnect. It turns out, at least in my experience, on a printed circuit board, because the wires are, those copper wires on the printed circuit board are fairly thick by, standards of something that's on chip. They're fairly wide. They're made out of copper, which is, fairly low resistance. The thicknesses of the printed circuit board stack that you're building, I'm assuming you guys have all seen printed circuit boards and stuff, are fairly thick. So anyway, like the resistance, the capacitance, I feel on a printed circuit board isn't that important, but inductance starts being much more important. And the reason is that the lengths are longer, and it's important to control the inductance. So anyway, just for your information, but on chip, we're really worried about resistance and capacitance. Okay, so now the first thing that's kind of confusing about let me just sort of talk about no, I don't know how to approach this, because this always tends to confuse people. Okay, the upshot of what I'm about to say is, when you're doing design on a chip, you are always trying to come up with numbers that are easy to deal with. You're trying to get rid of extra dimensions. An example is when we're talking about the sizing of a transistor and an inverter. Notice a lot of times on these tables in the book, it's talking about capacitance per micron. Why is that? Well, the reason is almost every logic device, any digital device, is going to use minimum length devices. So they just take that as granted, that your L is whatever's the minimum in this process, and you're just going to change the width. So they're not going to talk about capacitance per micron squared, which is really the appropriate thing to say. Like when I was just talking about the numbers for the 0.18 micron TSMC, the C sub G was given in, was whatever it was, 1.67 femtofarads per micron. Again, they just cut out the extra dimension and assumed that your length was 0.18. So, and designers are constantly trying to do that, so they only keep track of a few numbers. And why is that? Because of the complexity of what they're trying to design. They're constantly trying to simplify what they're doing because they have a lot of individual components to deal with. And resistance of wires is the same concept. So if you really look at the resistance of say a block here, okay? So you guys have all sort of had your basic physics here, but basically you have you have a resistivity, say if this is an aluminum block or something, right? You have a certain resistivity for aluminum. And if you're looking at the resistance of this guy, so the longer this guy is, assuming you're getting the resistance from here to here, longer resistance is, the more the resistance. And then you have this cross section, and the bigger this cross section is, the lower resistance. So you have the thickness times the width. So L makes the resistance go bigger, thickness times the width, or this cross section area reduces the resistance. And you got to multiply it by this resistivity, which is a function of your actual metal you're using. So in silicon, though, when you're doing chip design, I shouldn't say in silicon, when you're doing chip design, you have no control over this thickness. This thickness is just a given. It's whatever the foundry is making the thickness of this. You can't say, I want to make my metal one double this thickness. It's just not allowed. So this thickness is a constant for a particular metal layer. So what people talk about is they basically take resistivity divided by the thickness and call it R, they call it sheet resistance. Okay, R, whatever you want to call it, sheet resistance. So it's all it is the resistivity divided by the thickness. And why are they doing that is because now, if when you're looking at this this guy, let's say from the top down, as a designer, you're going to see that guy as being like that. It's going to have a length and a width. So basically, instead of keeping track of the resistivity of aluminum and the thickness, so this metal one line, let's say we're using metal one as an example, you just remember that the sheet resistance for this is, I don't know, 1 milliohm per square. Okay, that's how it's given. It's a weird value. It's in ohms per square. And the only reason is, again, you'll see how this makes this calculation easy. So let's say this L is 10 micron and its width is 1 micron. Okay, so this, you could think of it as being 10 squares, right? L divided by width is 10. So it's like almost like I could fit 10 squares. Each one of these squares has this value. Okay, so I just multiply 10 by R squared and I get whatever the heck is 10 milliohms total resistance from here to here. Okay, now let's say if this was this square was, if it was 10 centimeters by 1 centimeter. So what is that? 100 times bigger in each direction, exactly. 100 times bigger here, 100 times bigger here. So how many squares can I fit? By squares, I mean width over length. So a square would have one dimension would be the width, and the other dimension would be also the width, and how many of those you can fit. And this one I can fit in L over W of 10 over 1, so I can fit 10 squares. Well, guess what? The resistance from here to here is exactly the same resistance as from here to here, because the things have shrunk from both sides, the same number from both sides. So the resistance across from here to here is the same. So all I would have to do is to figure out, when I'm doing a layout, all I have to do is figure out the ratio of width to the length of the line that I have and multiplied by this sheet row, which is given per, I just have a table sitting in front of me. And for this particular process, there's a different number for each metal layer. So that's all you do, is you count it up. So for example, in this example here, these two, this and this, have exactly the same number of squares, because we've doubled things up in each direction. And so it'll have the same resistance. Any questions about that? This tends to really confuse the heck out of people, talking about this sheet resistance in ohm per square. So a square, the reason you're calling it square is because you're multiplying it by a sort of an aspect ratio of whatever line you have. No? Okay. So that's sort of the, when you see like design rules, it'll be, you won't see like resistivity and thickness, you'll see ohms per square for each metal line. So, and then you just multiply it by this aspect ratio, whatever metal line you're putting your interconnect in. Okay, so there's a few different choices of metals on a silicon chip. And basically you're left with really aluminum, which is sort of a classic, what people were using for many years, and they still use for some of the top layers. Okay, like an older process still uses all aluminum. At some point, people decided that aluminum's resistance was giving, like as you go into finer and finer geometries, this was, you know, they figured they needed to find something that's a lower resistance than aluminum, lower resistivity. And they settled in on copper. And I'm not sure exactly why they jumped into copper. I mean, I guess it's a low cost metal. It's used on like printed circuit boards, etc. So copper ends up being, you know, the metal of choice for a lot of tighter processes, especially the lower metal layers. So let's say if you have a 8 metal process, like layers metal 1 through metal 7 will be, you know, copper, and metal 8 will still be aluminum. The reason for that is because there is, you know, copper tends to be corrosive to silicon dioxide. So what happens is copper diffuses into oxide, etc. So nobody wants like bare copper in your silicon processing equipment. So basically, you know, they make the inner layers copper and they sort of cap it with aluminum essentially. So when you're getting the wafer, that unprotected metal 8 that, you know, you wire bond to is aluminum and it's not copper. Okay. Now that, and they didn't, you know, gold, sometimes people plate stuff with gold and it's like very rare. It's just an expensive thing. The good thing about gold is it doesn't oxidize. Okay. So it's like you'll see people wire bonding with gold. Aluminum oxidizes, and why is oxidization important? Well, usually the oxides of these metals are non-conductive. So if you want to make a connection to a copper and it's oxidized, it's basically a dielectric, so you won't be able to get a connection to it. Okay, you got to do something like soldering or something like that. So the nice thing about aluminum is it does oxidize in air, but the aluminum oxide is extremely a thin layer. So you can break through it very easily. I mean, it's like a very thin layer. So if you're doing wire bonding, etc., it's very easy to break through aluminum. So that's nice, but it's not the case for copper. It's kind of a annoying thing. So anyway, people went from aluminum to copper in the tighter processes. But the problem with copper again is that it's basically it's corrosive, it's diffusing the silicon, etc. So one is you got to basically still cap with aluminum, but even inside these metal layers, you got to basically, it's weird. You got to put a diffusion barrier around your copper. So what does it look like? Let me show you a cross section of what it looks like. So say this is a cross section. So I'm looking, like if I've cut the chip, I'm looking at this. So this would be, say, the silicon, and this would be a copper line going into the page. So what you have to do is to create this barrier around the copper so that the copper isn't really see our silicon dioxide intermetal dielectrics or anything like that. And so, you know, that's something that people came up with, but the problem is that this barrier takes away. So we said that the resistance is dependent on this, you know, this cross section. The bigger this cross section, the lower the resistance. Okay, the problem is, and this is a cross section, is that this barrier that we have to build, you know, in this copper is eating into our cross section. So now instead of this being the cross section, only this is the cross section. So it's turned out that the improvement in terms of the actual resistance of the lines hasn't been as good as the ratio between the bulk resistivity of copper to aluminum, but it's still been an improvement enough for copper to be now the dominant resistance, the dominant metal in the tighter processes. So you'll see it constantly, copper being most of the finer line processes are running on copper. Okay, so let me talk about the contacts. Okay, so we've been talking about the resistance of a metal line, but actually the contacts, which is where, so the contact would be, let's say I have this metal one, and I want to connect it up, and we always have to do this to be able to route stuff around, is let's say I want to contact it to a metal 2, and this is, so this would be, say, what's so-called via 1, and then metal 2 would get contacted to metal 3 via the layer called via 2. It turns out that these connections in between the layers, whether it's vias, and then we contact down to, so say, poly or diffusion with so-called contact. These things have like a very high resistance, relatively speaking. So each one, you know, these things we're talking about, you know, these lines, etc., we're talking about like milliohms per square. Here, where each one of these things is like 2 to 20 ohms. So it's a crazy amount of resistance when you think about it. You bleed and sweat to get this metal line lined up, so it only has like, you know, 0.1 ohm of resistance from A to B, and then you got to drop this contact that has, you know, 10 ohms of resistance, and it just sort of ruined all your work. So what you do a lot, what you'll see a lot, is you try to drop as many contacts of vias as absolutely possible. So if you have a certain overlap, you know, you could have just put, strictly speaking, one contact here. So this is, say, metal 2, and this is metal 1. Theoretically speaking, one contact would have given a short between these two lines, between the metal 2 and metal 1 and metal 2. But basically, you try to fill this overlap area with as many via connections as you can to reduce this resistance, 1. And 2, it turns out that via and contact failures, while they're extremely rare, there's still a much higher failure probability than some other bad event happening. So, and usually it's an open issue. So basically, if you had drop one contact here, a certain percentage of your devices would fail because that one contact would fail. And so now you've got a chip with 10 billion transistors and blah 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 that doesn't work because one contact fails. And again, you got to think about like what a low probability event that can be and still get you, because you have so many billions of these contacts in your chip. So again, what you do is as soon as you drop your second contact, your probability that two of these things will fail right next to each other is astronomically lower, and let alone if you have 16 of them sitting next to each other. So now you're pretty much guaranteeing that you're not going to have a yield limiting situation here. So like a good way to get slapped across the head when you're a new chip designer is to have a lot of single contacts in your layouts, because well, I got the connection, so life's good. But a senior person looking at your layout would immediately go, well, look, this is not going to get a high yield, or this is going to have a really high failure rate somehow. Okay, so those are the examples. And so I don't know, this example, I'm gonna just, you guys, is pretty simple, but I think this is what I wanted to maybe use an example of, is if you have something that is x wide and x long, all you have to do is then multiply it by this ratio by this resistivity of whatever metal line this happens to be. I don't know what this example, it doesn't say what the metal line is, but it's sort of a particular sheet resistance in terms of 0.1 ohms per square, and that's kind of typical. And all you have to do is multiply this length times width by this number, and you get the resistance. So it's just a smaller step. Okay, so this is like basically, the methods of reducing resistance. Again, you go to better materials. So you'll see that all the time where you're in copper and you try to put stuff close to each other physically. And you want to use more interconnect layers to reduce your resistance, but there is a trade-off with that, because more interconnect layers means a higher cost per wafer. And so, okay, I've like reduced my resistance, but I've increased my cost. So like a lot of things, it's a trade-off in terms of expense. And then you got to also, the other thing I want you guys to sort of, hopefully it'll stick in your head in terms of I'm hoping there's very few things you remember from this lecture. This graph of the nature of interconnects is something you should remember. And this you see on a lot of things. So there's a lot of, like we said, there's a lot. I mean, this is length of the interconnects, and this is the population of the number of nets that have that length. And you see that you have a lot, and this is log scale. So you have a lot of local interconnections and very few global interconnections. So when it comes time to these resistance and stuff, this is really where you're gonna get stuff you should worry about. Because if you got something that's like 10 microns long, it's just not gonna have a lot of resistance. So it's not gonna burn you. But it's like these kind of things that are gonna be problematic. And the nice thing is there's a few of these, and if you do like a sort of a hierarchical design where you're limiting the number of these connections and you're trying to create as many connections as you can locally, you solve a lot of your problems. So by doing sort of hierarchical communication, doing a lot of the work locally, keeping the inter-block communication to a minimum, you're really helping your resistance. And I think this is something that you see. I'm not a programmer or anything, but I think in a lot of a lot of designs, whether you're building software, firmware, digital design, analog design, doing things in a hierarchical way solves a lot of ills because it's just much more lower energy to build type things that are it's more robust from a standpoint of things breaking, miscommunication happening, verification required for the overall design. You can focus on small blocks, build them tight, make them tight, and whether it's the resistance you're reducing, or I don't know, like again, I'm assuming like if your if-then statements or whatever is tighter, is just like a really good design methodology to do that. And you see that across all sorts of, at least in electrical engineering, as far as I've seen, and I'm just guessing it'll be true in all sorts of engineering disciplines. So doing things hierarchically is really your best weapon for reducing resistance, and I think lots of things. Okay, so here are, it talks about different polysides, etc. I'm not going to get into that. It's like, so getting into the details of, polysilicon, how you reduce the resistance. Let's just say if you add things to polysilicon, you can reduce the resistance, and there's different materials that you can do that with. I think that this is a key table in terms of typical sheet resistances. And again, you can see that I think the key thing I want you guys to take from this is that, say, whether you got aluminum or copper, you have a certain resistance that it's in the 0.1, 0.05 ohms per square. But you can, and you will be tempted to, if you're doing chip design, to start routing things in poly, or even at some point you go, well, my N plus diffusions are conductive, I'm just gonna route this drain to this drain, of two transistors that are not sitting next to each other. I'm run out of interconnect path. I've sort of painted myself into a corner. So I'm going to route something with a poly, or route something with a diffusion, or even a well, because these are all conductive to some extent. But this is the problem that you're buying for yourself, is look at these resistances. So going from aluminum to polysilicon to diffusion or something like that, or God help you, a well, you have a very high resistance between 2 points, and you may not catch that when you're doing your simulations. And there's like extraction tools that feed back these values to you, but they tend to be time consuming to run, etc. So some people take shortcuts while doing extraction, etc. So all your tools may tell you you're okay when you're doing your simulations or verification, that point A is connected to point B, but the problem is it might be connected with a very, very high resistance and may be running nowhere close to the speed that you need to have it run. So I think the moral of the story is, anything other than metal lines, I mean, sometimes you will route stuff very short lines in polysilicon, but just like really do it with a lot of caution, and don't go here with wells and diffusions is my advice. So just try to use metal as much as you can. Okay, so that was a sum total of stuff on resistance. Now we're talking about capacitance. So just as we talked about, resistance, we were talking about, well, you've got this line, and this cross section reduces the resistance, and the length increases the resistance. When you think about capacitance, one really simple model is a parallel plate model. Okay, so basically the idea is you have a metal plate sitting over a infinite substrate on some dielectric, and there's a dielectric of certain thickness between them. And the model for the capacitance of this to this is this dielectric constant of this dielectric divided by this thickness times your width times length. Okay, that's your parallel plate model of capacitance. Okay, now it turns out that this is only marginally, well, still pretty useful when you're doing chip design. The problem is when we talked about, again, going back to, so notice that there's no mention of this parallel plate model. There's no mention of this height because it's just assumed to be insignificant. Now, this is a plate, it's pretty big. This is thick, this is thin compared to width and length, etc. So there's no mention of the height of this guy. Now the problem with this model is that, going back to our scanning electron micrograph cross sections, is you see how the actual cross section of a metal line looks pretty different than that. It's actually, this height is very tall and not very wide. Okay, and if you've, I don't know if I can't sort of zoom too much here, but let's say, for example, this was the dielectric thickness. If you look at this height, it's as much as your dielectric thickness. In fact, when you get to these two guys, this thickness that we ignored is much more than this dielectric thickness between the metal lines. Okay, so the problem is that this drawing is pretty lame when you compare it to the reality of a modern process. So what if I was going to draw this in a modern process, it would be something like this, okay, over this line. So, and the problem with that is now we've got a lot of what we're not showing here. Again, I'm assuming you guys have had E&M classes, etc. You got this fringing fields from these edges, and depending on how thick this is, how high this is, these could be significant or not. If this is pretty thin and this is pretty thick, then you just, most of what you worry about is these electric fields, but not so much about the fringing fields. But in reality, you actually have to worry about the fringing fields. And so in a typical line, in a VLSI design, the fringing fields, you have to worry about both the parallel capacitance, which is a function of how wide your line is, and the fringing fields, which are coming from the edges. And that doesn't matter how wide your line is, because you still have the same two sides. So basically, then you have to keep track of the parallel plate capacitance and the fringe field capacitance. And also, it's not just the capacitance. So in this model, this would be your metal 1, say, and this would be your silicon, and the metal 2 would have capacitance to the silicon. But in reality, you have to worry about the capacitance, your capacitance to other metal layers on top of you, say. Let's say this is a metal 2, there might be sandwiched with a metal 1 and a metal 3. It's going to have capacitance to either one of these, and let's say you're routing other metal 2 lines next to it, and you're going to have also capacitances to those guys. So you have to consider all these capacitances for a line. And we'll see what your options are for that. So, but anyhow, so again, to make things simpler for chip designers, what you end up with is a table like this for a particular process. And so this is basically a table that says in these guys, the rows, are the line, and this is the capacitance in area. So this is in some unit, probably in, attofarads. So femto is 10 to the minus 15, atto is 10 to the minus 18. Okay, so it's probably in attofarads. This is the parallel plate capacitance. So this would be metal 1 to the substrate. This would be metal 3 to metal 1. Okay, so it'd be, and this is the parallel plate value, and this in the bottom is the fringe value. So this is given in micron squared or per unit area, and this is just given in terms of per unit length, because the fringing capacitance, again, you only have two sides regardless of how wide you are, and this thickness isn't going to change. So this you just give in terms of per unit length, this total value, but then the designer has the option of making this wider, so the parallel plate capacitance can be bigger, and you have to multiply that by your area. So you have to basically keep track of both of those numbers. And again, this has this weird effect of having the fringe capacitance is given per unit sort of linear dimension or per micron, whereas the parallel plate is given in terms of micron squared. Okay, any questions about that? Again, I know that can get a little confusing about fringe capacitance versus parallel plate capacitance. So I think the main thing is the parallel plate capacitance will depend on how the sizing, how wide you make your line width and length, whereas the fringe capacitance is only a function of the length of your line. Okay, but you have to, they're both important. Okay, let's see what I want to say about this stuff. Another thing that you might hear about is used to be in older processes, the intermetal dielectrics were all silicon dioxide. And again, so this is, we're always trying to reduce capacitance, reduce resistance, reduce capacitance. And so since this dielectric value, the higher the dielectric constant of the material, the dielectric we're talking about, the more the capacitance. So people were looking for and have found these sort of lower dielectric constant, so-called low K dielectrics, to use as the as intermetal dielectric, to have like a dielectric constant less than the silicon dioxide. Even if it's, they go through a lot of pain to go from 3.9 to say 3, but I guess it's still worth it. And then, one of the interesting things is they use air pockets. So there's just like nothing sitting there, just air in between lines. So hard to visualize. I want to say about this. So the other thing is that, we're talking about, just as the resistance of diffusion is very large. If you look at, so let's say if I'm going to draw so this is your transistor. So N plus, this is poly. So, and let's say I was going to route this N plus to another transistor because I'm looking for trouble. Okay, just as the resistance of this is high, so is the capacitance of this thing, because this guy has capacitance of this basically junction is all capacitance. So it tends to have a very high capacitance. So it not only has a high resistance, but it also has a very high capacitance. So, don't use it for wires. If for God's sakes, don't use it for wires. I've seen it. I've seen it in NASA. I've seen it in commercial companies. I probably have done it myself and have conveniently forgot, but like, don't do that. It'll be very tempting. The reason it'll be very tempting, again, it's very hard to imagine what kind of problems you'll be running into when you actually start trying to interconnect all your devices. You're gonna end up painting yourself into a corner, even if you have 8 metal layers. It's called routing congestion, and you're trying to connect all this stuff. And at some point, you know, midnight on a Friday night, you got to get your chip out, and it'll be tempting to run something in poly or diffusion or something like that. But it's just very high resistance, very high capacitance. So try to avoid it as much as you can. Okay, so this Elmore delay, you know, I'm not gonna do this model, but it's sort of, well, maybe it's just be worthwhile doing it. So again, it's talking about using a, you know, this is using a single pi model of, remember again that this pi model is very, very effective in terms of emulating the continuous resistance capacitances. Where is it? Yeah. And so, you know, 3-segment pi model is very, very accurate, but in this example, they just used 1 segment, which is better than nothing. But where is it? Yeah. So it's just using an example of an Elmore model. So this is the resistance of your driver, and you know, it's 1,000 ohms for, you know, that's your inverter. So that would be like your NMOS trying to pull this line down. This is the gate capacitance. So if I was going to draw the schematic of this thing at a very high level, it'd be this guy, and there'd be some routing, and then there'll be driving another inverter. So this guy is basically, so this guy is this guy, this guy's gate capacitance is this guy, and this wire is this guy connecting the two. And to come up with an estimate of the resistance, you can just use the Elmore delay, which is this times that plus, so this times that, plus this times that. So that guy. Okay, and then you can stop there. If you just had more segments, you just sort of, you know, do the same Elmore delay estimate. Okay. All right. Let's see. How far do we have to go? Oh boy, crosstalk's pretty important. So let's just say, so that was in terms of the delay caused by resistance and capacitance. Okay, you basically come up with the total capacitance of a line, come up with the total resistance of the line. You look at what's driving it. You look at the, you know, the end load, and you can use something like an Elmore sort of calculation to come up with an estimate. So that's in terms of the delay. Now, another problem that capacitance gives you is crosstalk. So just as we said, you know, you have in sort of a fantasy scenario, you just have a metal line sitting over a substrate. In reality, you have like a metal line sandwiched between a bunch of other metal lines, which are going to have potentially their own signals running through them. And some of these signals may be high-speed signals. And some of these metal lines could be running very close to you. Say this is a bus, and you had a limited width of an area to run your bus through. And all these, you know, these were the various bits on the bus. So this would be like bit 0, bit 1, bit 2, etc. And now these guys are all sitting right next to each other and potentially have high capacitance between them. And that, as we'll see, that high capacitance can basically create a crosstalk situation where a you can basically get, you know, like one bit on the line corrupting another bit, and you have to be really, again, I've seen that happen in high speed designs quite I should say often, but you know, I've seen it enough, you know, once every couple of years we see that, and it's really, really difficult to debug and fix. So anyway, we'll come back and talk about that on Thursday and finish up interconnect then. Any questions, guys? Okay, if not, I'll let you guys go, and good luck on your project.
All right.
Take care.
See you Thursday.
Thanks. Bye.
Thank you, Professor.
Thank you.